comes to surface integrals, sometimes you're able to write down z in terms of x and y. So any surface like S with equation z equals to g of x and y can be considered as a parametric surface. Well, in this case, you might say, hey, what are the parameters? You can say that x is equal to x, y is equal to y, and then z equals to g of x and y. So in this case, partial derivative of r with respect to x is going to be 1. And, well, it doesn't have any y in it, so it's going to be 0. And then partial derivative of g with respect to x itself. So you have x, partial derivative with respect to x is 1. Partial derivative with respect to x is 0. Partial derivative of x of z with respect to x is going to be partial derivative of g with respect to x. You're just going to copy down the whole thing. And then partial derivative of r with respect to y is going to be, now it doesn't have any y in it, so it's going to be 0. This is with respect to y is 1. And this guy with respect to y is partial derivative of g with respect to y. Now you can find the cross product between these two, rx plus ry, which is equal to, well, I, j, and k, 1, 0, partial derivative of g with respect to x, 0, 1, and partial derivative of g with respect to y. Can do the computation. This guy is equal to I is going to be 0 minus partial derivative of g with respect to x minus j. Here you have partial derivative of g with respect to y and then 0. And k, if you think about k, this is just 1 and this is going to be 0 plus k times 1. So this is nothing but negative partial derivative of g with respect to x and negative partial derivative of g with respect to y and 1. Very good. So now you can find the magnitude rx plus ry, which is nothing but square root of this guy squared plus this guy squared plus 1. So you have partial derivative of g with respect to x squared plus partial derivative of g with respect to y squared plus 1. Perfect. So the surface integral of function f in x, y, and z ds over s can be written as the partial derivative, the double integral over region D of f of x, y, and then z is just a function in x and y. So here you have g of x and y, and then you're going to take this magnitude and we have it as square root of partial derivative of g with respect to x squared plus partial derivative of g with respect to y squared plus 1 and d. Let's take a look at a quick example to apply this formula here. So in this example, you have the following scenario. I ask you to evaluate double integral of y ds over s, where s is the surface. So this surface given to us is z equals to x plus y squared. X is bounded between 0 and 1. Y is bounded between 0 and 2. Okay, perfect. Very good. So as you can see, z is a function of x and y. We have a nice formula to follow. Let's see what does it give us. The double integral of y ds over s can be converted into double integral over region d of y and ds. So instead of ds, you're going to compute this radical dA. So here you have the square root of, but what is partial derivative of g with respect to x? It is just 1, so you get 1 squared plus partial derivative of g with respect to y. It is 2y, so you have 2y squared plus another 1, and here you have dA. Very good. So this double integral is equal to the double integral. X is bounded between 0 and 1, y is bounded between 0 and 2, so x is bounded between 0 and 1, y is bounded between 0 and 2. We have fixed boundaries, and here you have y times square root of 1 plus 1, which is 2, 2 plus 4 y squared dy dx. Here you can factor out, for example, 2, and you have square root of 2 in front of integral, or you can just say that, hey, I want to take this guy as my u. Either is fine. So if you take u to be 2 plus 4y squared, du is 8y dy. So you get 1 over 8, integral 0 to 1, and here you have the integral of u to a half du dx, which gives you 1 over 8, integral 0 to 1, and here you have plus 1, so you get 3 halves, 2 thirds, and your u, which is 2 plus 4y squared, 3 halves, and your y is bounded between 0 and 2, then dx. And we have different techniques, different method computing this. And eventually, if you simplify this, remember that you don't have any x here, so you could just say I have integral 0 to 1 of dx, which is just 1. So far you have 2 thirds, and here you have 1 over 12, and I just do the substitution here. You get 2 plus, here you have 16, so here you have 18 to power 3 halves minus, if you substitute 0, 2 to power 3 halves, and you could simplify this more, or you can eventually use your calculator to evaluate or approximate this number.